My name is Muhammad Tariq, and in this lecture, we'll apply the path compression technique using find method. We have implemented find union, and we have seen how this operation is going on, how we can union two disjoint sets. And in this lecture, we are going to see how what changes we need to make in the find method to apply the compression. The advantage of path compression, as we know, that it reduces the height of the tree and we can directly access the parent or the representative of the node using the constant time, right? So now we have this set of unions here, and now what change we need to make is we will, instead of returning this value, we will contain this value in an integer. Let's say integer result. We will contain this value, and then we will assign that value to the array of I, whatever the index is, and we will assign this result to that. Now I will explain you clearly how it's going, how it's working, and then we will return the result. Okay, so now let's apply union to some of the to this set. Okay, if I draw the picture of this set, so I can draw something like this. We can visualize this union. So we have 0 and 1, so I have something like 1 and we have 0. So the representative or the parent of 0 is 1. So in the same way, we have 3 and we have 2, right? And for 4 and 5, we can say 5 and we have 4. And now 3 and 4. For this operation, 3 and 4, 3 is the parent of itself, so there is no issue with that. 4, for 4, the parent of 4 is 5, so the union will be this, right? So now let's implement. I'm not implementing the last one, and this with when we will apply this operation, when we will perform this operation. So here is a candidate for path compression, which is 4. So this 4 should be connected to 3, right? And how it's going to work, I will show you that. So let's apply union djs dot union, and we will union 0 comma 1, right? djs dot union 2 comma 3, djs dot union 4 comma 5, djs dot union 3 comma 4, and let's say djs dot union comma 2. Okay, so we have this union set, and then we can check if djs dot find, let's say find 4, if that is if the parent of 4 is equals to djs dot find, we can say 0. If their parents are same or their representative are same, so we can say system dot out, we can say true, otherwise we will print false. Will print false. So let's apply a breakpoint here. Let's apply a breakpoint, let's say here. Okay, and let's debug this file. Okay, now we are standing here on line number 59, which is this one, and let's apply breakpoint 1 in union and 1 in this find method. Okay, now we are in union method, and this will be, so the values of I are 3 and 4. So now we will first find the parent of 3, and parent of 3 is if let's check this table also. So this is the runtime, this is the the structure of array at runtime. So we can see the value of 3 is 3, right? So it means 3 is a parent of itself. And if we check the value of 2, the value of index number 2 is 3. We can see here that the parent of 2 is 3, same like the one we have in in this diagram we created, like the diagram we made. So this runtime structure is also verifying our diagram. So in the same way, as you can see here, the 5 5 is the parent of itself, so it's a self relation, reflexive relation. And 4, index 4 is a child of 5, and 5 is a representative of 4. So in the same way here, 1 is the reflexive, is self reference, and 0 is the parent of 1. Sorry, 0 is the child of 1. So this runtime is verifying our picture, our diagram. So now let's move forward. We are in the find method. It will return the same one. Now let's check the parent of 4. The parent of 4 is 5, as we know. So now we are applying union on the 5. 5 is the value 2 and value 1 is 3. So we are joining 3 with 5. So like this one in this figure, as we join 3 with 5 like this. Okay. Okay, now we are now on the instruction on the code which is joining the 1 and 2. We are applying union on element 1 and 2. So as we know with this diagram that we have 1 is the self parent, 1 is the reflexive or the self relation, and 2 is actually 2's parent is 3. So now let's see what happens. So now here we are, the index of I is 1 and the index of j is 2. So 1 is the self parent, so it is, this line is pretty easy, with is nothing complex. So we will move to find, and find will return itself. Now for value 2 we have j is 2, so j's parent is, now we are in the else part. In the else part, the parent of 3, sorry, the parent of 2 is 3, as we know. So now with this recursive function we got the result as a 3. Now we can return 3. Now the pointer will come on line number 35, because now we have written some line which were not executed, because this was a recursive call. So now after returning this, so as you can see, the pointer came here and the result is 5. So it's actually something like this. If we draw the array here, so if I draw the array here, I have the array and I have the values, index values 0, 1, 2, 3, 4 and 5. And so here for 0, the parent of 0 is 1, parent of 1 is 1, the parent of 2 is 3, the parent of 3 is 3, the parent of 4 is 5, and the parent of 5 is now actually 3. So this is the current position of the array. And now what we did, now 1 will be pointing towards 3, right? 1 will be pointing towards 3. Sorry, so the 5 is pointing towards 3. So this is actually, as you can see, we have result 5, and here I is equal to 3, right? So now this is actually index number 3 is pointing towards, or you can say the index number, so the index number 3 is pointing towards 5, right? And if I show you this, if we see this runtime array, so the value of 3 is pointing towards 5, right? So we can change this here. So the value of 3 is pointing towards 5, and 5 is the representative of all these elements. Okay, we can change this self reflection here, from here to, we can change that to here. Okay, so this is this self relation, the reflexive relation. Okay, now if we move forward, so now we are here at line number 45, and now we can union, which is 5 and 1. So index number 1 is now pointing towards 5. So this will be the relation, something like this. We make the relation. So now this one is actually pointing towards 5, or I can draw this here. So as you can see, the value 5, sorry, the index number 1. Now the index number 1 have the value 5, right? So we can change the value now. We can change this value here. So we can change this value and we can write here 5. Okay. Now if we check in this runtime array, so we can see that index number 1, as you can see, is pointing towards 5, as in our index in our array also, and index number 3 is pointing towards 5. So index number 3 in our array is pointing towards 5. Index 4 and 5 are also pointing towards 5. We have two indexes which are not directly pointing to the parent, or you can say the representative of the set, which is 1 0, sorry, which is 0. 0 is actually pointing towards 1, and index number 2, which is pointing towards 3. So we will apply path compression on these two indexes. Okay, let's move forward. Now we are going to compare two values. Now we are going to compare 4. As you can see, 4's parent is 5, and the second is 0. Okay, so for 0, 0's parent is 1. So now let's see what happens. So first, find 4 will be called. So now let's go into this method. So here I is 4, and when we will apply this condition, so the parent of I is, and the parent of 4 is 5. So this condition will be false and the pointer will come in the else part. So as you can see, the execution pointer has came in the else part, and now what will happen is, this will, the parent of 4 is 5, so it will go back. Now it will return 5. Okay, here is 5, return 5. We already have 5 here. Okay, on index 4 we already have 5, so it will run, this doesn't change the values of this array. So now 5 is assigned to index 4, which we already have. Okay, now let's see 0. Okay, this is the interesting part, and we will be focusing on this when we will see the 0. So the 0 is actually, the 0's parent is 1, and then 1 is pointing towards 5. So we have this path we can compress. Now the I is 0, so this condition is false, so we came in the else part. Let me draw the stack here for your convenience, so we can also track what's actually going on. Okay, so what we have here in the code, so the parent of 0 is 1. Okay, so the result will be, so here we will so actually here we have 0, here is the first element, we have 0 here, right? And now this is a recursive call, so the method will go back. Now the value of 0 is 1, so now I will be equal to 1. So now as you can see, the value of I is 1 now, right? Because I is the parent of 0. And what is the parent of I? What is the parent of 1? The parent of 1 is 5. So this condition is again false, and will come back in there in the else part. So as you can see, the pointer has came in the else part, and now we will check the parent of 1. So the parent of 1, we have 5. So now here we can write 1. Now the parent of 1 is 5. It has gone back, and now i's value is 5, because the parent of 1 is 5. So now this is true. Okay, so this is true. As this is true, it will return 5, right? So as it will return 5, now it has came back here. So the result of 1 is actually 5, right? So we can say, so the return, what is returned? 5 is returned from 1. 5 is returned from 1. So here in the code, result, which is 5, and it will be assigned to 1. Okay, this is 1. So it, because now it's the recursive, is going to, uh let me write it here. So as you can see, the parent of 1 is 5. Okay, the parent of 1 is 5. So 5 will be assigned to the index number 1, and then it will go back. So it's recursive, so it will come to the next element of the stack, right? So this will pop out, the 1 is pop out, and then the pointer and the control will go to the next element. So here in the code, 5 is assigned to the 1. So if we see here, we already have 5 or assigned to the index 1. So this is there is no change. But then after this, it will compress the path. Let's let's see in the code. So it will return 5. And now you see the pointer has came again on the line number 33, because now the value of I will be 0 now, right? The value of I will be 0. Why it's 0? It has, as you can see in the figure, it has came on the value 0. It's the pointer has, because the stack has an element in, the stack contains an element, so it has came to the element 0. And now in the code, result is same, because the parent is the same. So now we will compress this path and we will assign 5 to I, which is 0, right? So we can change here the 0, we can change in this array from 1. Now it's referring to 5. Okay, it's referring to 5. And now if you can, now the pointer, there is nothing available, so the stack has been completed. And now in the code, if you see, we came here, we came back on the original location from where we called the find method. So as you saw how the compression worked and how it compressed, so now I can, in this figure, I can remove this line and I can directly connect 0 with 5. So in the same way, this 2 will be, we can compress this path, and in the same way this 2 can be referred directly to the 5, which is the representative of this set. You have, I hope this will be helpful for you and you have understood how this actually working. I will strongly recommend you to practice this, to write the code on your own and debug the code and see how it's actually working. Try to explore the values at runtime. This will give you the actual idea of what's actually happening at the runtime. I will see you in next lecture. Thank you.